Alright, so we are going to look at section 5.7, which is integration, but we're thinking about inverse trig functions. So first we need to look at the rules, then we're going to try to prove one of them, and we'll do some examples. So let's see how this goes. So recall that your derivatives of arcsine and arccosine are these. So if you're thinking antiderivatives, right, then we can just take these and go backwards so that we go from here to arcsine, or from the negative of that to arccosine. So with that in mind, voila, we have our indefinite integral of 1 over a squared minus u squared, square rooted of that, and the reciprocal of that is arcsine of u, which is what we're integrating with respect to, over the absolute value of a plus c. And if you have the negative of this, then you're going to get the cosine, arccosine. If we're looking at a sum, then we're going to get out tangent, arctangent, and we're going to multiply by 1 over a. U over a is inside our arctangent, and we're adding our constant of integration, c. And if we're multiplying, if we have like this, but a little bit tweaked, so we have 1 over u times root u squared minus a squared, where u is what we're integrating with respect to. Then we have 1 over the absolute value of a, which is what we're subtracting out over here, times arcsecant of u, which is what we're integrating with respect to, over absolute value of a, and we're adding c. So that is the goal. We'll see how that goes. So let's try to prove that. How can we prove that? Well, we should probably think about what our we should think about our derivative, implicit differentiation-wise. So think about that for a little bit. Suppose we had y is equal to arcsine of something like x over a, where a is some real number. So our goal is to use differentiation, and that's kind of tricky. So maybe we can shuffle things around a little bit. So if we take sine of both sides, then we have sine of y is x over a. Multiply by a on both sides, we have a sine y equals x. So from here, we can take our derivative with respect to x, and it's not too bad. So we have what? A, which is a constant, right? It's a constant. So that's just a scalar multiple, and then we take our derivative of sine, that's cosine. So we have a cosine of y times derivative dy dx. And this equals the derivative of x, which is 1. And now we can rearrange this again to get dy dx by itself. So we have dy dx is 1 over the reciprocal of what we're multiplying by, a cosine of y. And we're taking cosine of only y. Okay. So we can also use the Pythagorean identities, where we have cosine squared, and let's go with y, plus sine squared of y equals 1, right? And then here we can solve for cosine. So let's cosine squared of y equals 1 minus sine squared of y, okay? And but the goal is to have cosine of y, not cosine squared. So we can resolve that issue by doing what? We can square root. So we have cosine of y is root 1 minus sine squared of y. And from here, we can substitute this value, this square root, in where we have cosine of y. So we have dy dx equals 1 over a root 1 minus sine squared of y. And now, well, it's like kind of tricky. We should probably put that a, like push that into our square root, a radical. So we have dy dx is 1 over root, what, a squared minus a squared sine squared y. Okay, but that's not too far off. A squared times sine squared of y is just this squared, so if we square both sides, then we can get this back in terms of x. So we have dy dx equals 1 over root a squared minus x squared. And so, well, that's really lovely, because now we know that when we find our antiderivative, then we just get back what we started with. So there you go, right? Because when we take our, let me do this, right? I guess we can massage this a little bit so the algebra looks a little nicer. 1 over root a squared minus x squared. I'm terribly sorry, this is heading into the corner. But see, now we have this, and so when we integrate here, we get y. When we integrate here, we get arcsine of x over a. So this gives us that when we're looking at 1 over root, like a squared minus x squared with respect to x, that gives us arcsine of x over a plus c. And that's not too terrible, right? The difference between the u and the x doesn't matter too much because we are armed with u substitution. So the variable that we're looking at here is x, but other times, you could be looking at some other function that you're using u substitution for, which we'll be using later. Ready to prove some of these in your breakout rooms, so that'll be fun. All right, so let's look at some examples. Well, the first one, that looks like it's that just looks like it's an arc sine. The second one, there's no square root, so which rule does that apply to? It looks like it's going to be arctangent. And the last one, we have an x being multiplied in front of our radical, so I think that's going to be our arcsecant. So try those on your own and check back in to see how we get. What would the answer for A be? So we have A, where we have 4, and so the square root of 4 is 2, and that's what we're going to use. So we have arcsine of our variable x over 2, which is the square root of what we have over there, and then plus c. It's not too terrible. Okay, fantastic. All right, so for B, though, there is a little bit of trickiness that's happening, because we have a 9x squared, which, if we're thinking back to our original formula where we're looking at u's, what could u be so that u squared equals 9x squared? Well, u can be 3x. And then, what about a? What would a be here? A is going to be, a squared is 2, so a is going to be root 2. And I'm going to take the principal root because it's helpful. So with that in mind, we can rewrite this as what? Du is 3 dx. And so wherever we see dx, we're going to put we're going to put 1/3 du over, and then this is a 2, which is root 2 squared, right? Plus u squared. And then in order for that to work out like nicely, right, then we need to do a little, wait, I got the u. Okay. So, what should we do? Well, we have, in our pocket, we have arctangent, right? So we can have this is going to be, what? We're going to have arctangent and 1 over a, right? So 1 over a is 1 over root 2. Arctangent of u over a, which is 3x over root 2 plus c. You know, I think there's a chain rule in here though, right? Because we do need to, yeah, because we have this, we do need to divide by 3. Let's see where that. Oh, because over here, forgot that. Okay, so we got 3, and we need a 3 up here. Sorry. Oh my gosh. Okay. So there we go. And this is going to be our. Yes, we did U substitution, and we looked at an A, which wasn't not a nice number, but a number nonetheless. And we did our U substitution with our arctangent, and then we got this as our answer. Oh my gosh. Okay. There we go. Okay. What about C? How are you going to do C? I think we need to do another U substitution. So we need U is going to be what? For U squared to be 4x squared, U is going to need to be 2x. And then du is going to be 2dx. So what are we getting? Well, it's almost nice. I guess we could multiply by 2 over 2, because that's multiplying by 1. You see I multiplied by 2 in the numerator and 2 in the denominator over here. And so, what does that give us? That gives us integral 2 dx, which is just du, over 2x, which is u, times root 4x squared minus 9, and a is going to be 3, right, because we have a 9 there. And so, this 2 dx is going to be du, and this 2x is going to be u, so we're left with integral du over u root u squared minus 3 squared. And what's that? That's arcsecant, right? So we have 1 over a, which is 3 arcsecant of the absolute value of u, which is 2x, over a, which is 3, plus c. And there we go. Boom. The tricky part is just doing the u substitution right and efficiently working. So this multiplying by 2 over 2, that's really nice, and that's effectively what we did here as well. That doesn't fit, which is kind of sad, because if u was e to the 2x, then du would be 2e to the 2x. And that gets us pretty much nowhere. So maybe we need to be a little bit more careful about what we're doing. Well, what if u was e to the x? And then du is e to the x dx, right? And that means that we can do what? Dx is equal to du over e to the x. And, well, e to the x is just u, so we know that dx is equal to du over u. Do you see what happened? That we had u was e to the x. So for e to the x, we could substitute it in with a u. So now we have dx equals du over u. Okay, so does that help us? I really hope so. So we have dx, so that's equal to du over u, and this is all divided by the root of u squared, because u equals e to the x, so u squared is e to the x squared. E to the x squared is just e to the x times e to the x. Same base, so you can add, so we have e to the 2x. There's a power to a power, you just multiply the powers, minus 1. Okay. Well, actually, that's not too bad, because that looks very much like arcsecant, sorry. So we have integral du over u root u squared minus 1, And this looks very, very much like arcsecant with a equals 1 and u is u. Okay, so then we have this is what? 1 over 1, which is 1, times arcsecant of u over a. Do we absolute value the u? So we got u absolute valued over a, which is 1, plus c. And what is that? That's arcsecant of absolute value of e to the x plus c. And e to the x is always positive, right? All the outputs for exponential functions, as long as there's nothing funky going on with them, is going to be non-negative outputs. So arcsecant of the absolute value of e to the x is the same as arcsecant of e to the x plus c. We can drop the absolute values because e to the x is always non-negative. Just if you don't remember, just draw a quick sketch of what exponential functions look like, justify it to yourself. Hey, that's never going to be 0 and never going to be less than 0. And there you go. How about this one? This one, it looks like we need to break it up. How are we going to break this up? And then use some good algebra to get us out of trouble. So let's see. If we do this is equal to integral of x over root 4 minus x squared plus 2 over root 4 minus x squared dx. And, well, this first one, that's just, that's what we were doing before with just substitution, right? And we can also break these up into 2 separate integrals, right? Because those are one of our integral properties. Okay, so let's see. If we have u over here is 4 minus x squared, that means that du is going to be negative 2x dx, right? And so we almost have that right here. And so we're almost happy. So we get what? This is equal to negative 1/2 du over u to the 1/2. We're integrating that. And that's not terrible. Let's see, that's power rule. So we have u to the 1/2 divided by 2, and it's a negative, so we got negative 1/2 u to the 1/2, and then dividing by our new power is the same as multiplying by 2 over 1, so that's that part, and those cancel, so we get this equals negative u, which is 4 minus x squared to the 1/2 power. That's just this part, okay? And then we have this part, which is slightly more new, and what do we have? Well, that actually looks very close to arcsine, where a is going to be 2, okay? So, what do we get here? We get plus, and if we take this 2 out, then we very much have arcsine, right? We have 2 times arcsine of x over 2 plus c. So this is what? 2 arcsine x over 2 plus c. And just copy down one more time. 2 arcsine x over 2 plus c. And so there you go. Was it okay that we were kind of lazy about our plus c on this side? Yes, because we had a plus c over here, and also here we have an indefinite integral, so this implicitly has an understanding that we have a plus c. Here, this was slightly sloppy, but we made up for it right here with our plus c, so we still end up with a family of functions, and there we go, final answer. I think that's out of frame. There you go. Okay. What about this one? We have, well, is that factorable? Is that nice? No, that's like really gross. Okay. Well, maybe we can think of something else. What else could we do? Well, do you remember completing the square? Where you're looking at, like x squared plus, I guess bx plus c. I guess we'll throw an a in there for good measure. Okay, so we're trying to solve this and it's not working and we're sad, so try to factor out the a. So we got b over a, c over a equals 0, and then completing the square means that we need to move that over, or just push it out. So we have like a x squared plus b over a x plus something, plus, I guess we just pull that out of there, because if you distribute your a to the c over a, then it just becomes a c again, okay? And then we want this to be, we want this to be a perfect square trinomial, so we need b over a, we need half of that. And then we need to square it like that. And then we're happy, because then we get, this is what, x plus b over 2a, and then we square that times a plus c. Yeah, seems about right. Okay, so let's complete the square here. We get, what, this equals integral. It's moderately difficult. Okay. We got dx over, what, x squared minus 4x. Minus 4x plus what is going to give us a perfect square perfect square trinomial? Is that what? Yeah, perfect square trinomial. We got what, 2? 2 squared is 4. And then plus, well, we want the plus 7, and we have a plus 4, so we do a plus 3 tacked on at the end, because 4 plus 3 is 7. Okay. So then we have what? Dx over x minus 2 quantity squared plus 3. And then we can make one of these a u, probably the x minus 2. And then this is just arctan. So that gives us arctan of x minus 2 over root 3. And then I think, do we need to multiply by 1 over root 3? Yeah, I think we do. Yeah, 1 over root 3. Oh, plus c. And there we go. Cool. Alright, last one. Well, because we were doing all of these, I guess, with indefinite integrals. So we can do this one with definite integral. What do we get? This is arctan of x over 2, and then 1/2 over here, evaluating from 0 to 2, using the fundamental theorem of calculus. We get 1/2 arctan of 1 minus arctan of 0. We'll leave that as an exercise for the viewer.